Health is an eternal topic for mankind. We are born on Earth, and our health is intimately linked to the environment and ecology. The environment is the basis for human survival and development, and every subtle change in the environment will eventually have an impact on biodiversity, ecosystem, and our health. Exploring how the environment and ecology affect our health in the past, present, and future is the mission of Eco-Environment&Health. Eco-Environment&Health is a journal initiated by prestigious scientists with a strong editorial board, including multidisciplinary scientists from all over the world. With the support from EEH, you will have a better publication experience. EEH has its own offices of publishing, language, design, and broadcasting. The experts will accompany you like a harmonious band and spare no effort to sublimate your valuable scientific research into a magnificent and impactful masterpiece. We have a dedicated center for decision-making that deeply integrates informatics, ecology, and environmental science. It explores global research hotspots, predicts discipline trends, monitors the influence and dissemination of publications, and supports the journal's smart decision-making. Upon receiving your submission, our assistant editors will contact you immediately and keep you informed of the manuscript status throughout the entire process. The 14-day rapid peer review will make the publication of your research one step ahead. Your distinguished work is worthy of being known worldwide. We will promote your research globally in a three-dimensional manner through various social media platforms. In addition, the open access fee will be waived for the first 3 years, making your research easier to be read and cited by your peers. We continue to explore and innovate the service strategy of the journal. EEH leads ecology and environment to a healthy future.
张老师好，
哎，古老师啊，你好！
你好，你好，感谢支持我们。
哎呀，这是应该的，应该。你们这个平台现在搞得越来越好了，
是吧？
嗯，
反正就是说，我们也经常能坚持住这样的1个星期2次的这样的一个频率吧。但是前一段时间因为环花大会啊，可能有点耽误。但是一般我们要坚持这个，还是不容易。反正我们尽量。
是啊，你这个很花时间的呀。
是的，
不容易，
也大家支持。差不多了，快到时间了。
你现在这个受到大家欢迎，我觉得参加的人越来越多了。
对，他们国内的人一般不太喜欢用 Zoom， 所以 Zoom 上面你看的不多。他们喜欢用在这个就是这个哔哩哔哩啊，还有那叫什么扣享平台上人特别多，都上千的，有的时候多的时候。因为现在对暑假的时间可能会受点影响吧，总的来说还好。OK， 我要不我开始吧，时间也到了。
好的。
Thank you. Okay. Good morning and good night, everyone. So welcome to Talk at EEH. So today our speaker is Professor Huichun Zhang. First of all, I would like just to give a brief introduction about Dr. Zhang. Professor Huichun Zhang is a Frank Neff professor in the Department of Civil and Environmental Engineering at Case Western Reserve University at USA. She get her PhD from Georgia Tech, and she is also alumni of Nanjing University. She got her a bachelor degree and master degree from Nanjing University. Her research focuses on the fate and transformation of environmental contaminants in natural and engineered aquatic environments, and the removal of organic contaminants from contaminated water. Her recent research area also include a predictive modeling for the contaminant reactivity and absorption using both classical models and also machine learning tools. So I think she will talk about this tonight. And also Dr. Zhang has published numerous journals, such as Chemical Review, ESNT, and Water Research, also for the Applied Catalyst B environment. She has received 6 competitive research grants from US NSF. In addition, Professor Zhang directed research projects for many other federal and state agencies and industry. She is a topic editor for the ACS, EST Water, and also associate for the FESE. All right, okay, let's welcome Professor Zhang to give the talk. So you can start now. Thank you.
Okay. So thank you, Dr. Gu. If you can allow me to share my screen. You might have to stop your current screen sharing. Okay, let me share my.
It seems like, yeah, okay.
Good. Okay, so it's working now.
Yeah.
Hi, good morning or good evening. Thanks to Dr. Chen for the nice introduction. And it's great to be back at the EEH, because I think this journal has been taking a lot of heat and also been gaining a lot of attention. So I believe this journal will be very well respected because of its excellent editorial team. So some of you might have been to my early talks about either modeling using machine learning tools in general, or how we model chemical reaction in different kind of settings. So today I'm going to focus on specifically how we model environmentally relevant chemical reactions with machine learning tools. This is going to be based on 3 of my recent articles being published. The first one is a review article talking about how to model chemical reactions. Basically, that's going to be the major topic for today. And then the middle paper here actually will not be published until probably early next week. It's being officially accepted, and it's in the proof process where we're modeling aerobic biodegradation. This is an example I'm going to use for large data set. And the last paper is going to be something we published a few months ago about 4 small data sets of oxidation. Here's the outline of my talk, where I first will introduce some motivations and then talk about the workflow of how we model chemical reactions. And then I will use 2 examples. One is a large data set for aerobic biodegradation, and then 4 small data sets for oxidation. And finally, some conclusion. So many of you who have been working with organic contaminants or contaminants in general should be aware that there are many reactions chemicals undergo. Here is an example of a typical wastewater treatment process, where we know when the influent come in is going to undergo primary sedimentation, active sludge treatment, and secondary sedimentation. Usually water is discharged into the receiving waters from here. But for more advanced usages and because of tighter regulations, this water will be undergoing additional treatment, such as ozonation, flocculation, filtration, adsorption, and UV disinfection, or other processes. So given a large number of chemicals we are facing going through all these processes, certainly it's important to know how fast they're being removed, the removal efficiency, and how we can further optimize these treatment processes. So that requires us to know the reactivity of different chemicals in different processes. Another example is, despite the effort to remove chemicals in these treatment processes, for now we have only a very small being regulated. So majority of the chemicals are still being discharged. So I'm using pesticides as an example. Once pesticides are applied to the field, they can be either ending up in the air, in water, or in soil. In air, they can undergo this photodegradation, even precipitation. In water, they're going to undergo hydrolysis, photolysis. In soil, there are more reactions being involved. There'll be absorption by crop, attached to soil particles, even runoff to lakes and rivers. They can be undergoing microbial degradation, leaching into groundwater, etc., etc. So overall, I do have this idea that there are so many reactions we have to worry about for many different contaminants. For sure, that means modeling is a necessary tool for us to understand their reactivity. So with that background in mind, I'm going to show you a workflow of how machine learning can be used to model chemical reactions. Some of you might be familiar with this slide of what I introduced earlier, which is based on a paper we published last year introducing machine learning as new ideas and tools. In that talk, I talk about there are mainly two types of machine learning approaches. One is called the supervised and the other is called the unsupervised. Of course, there's like reinforced learning, which is much less being used. I'm going to focus on supervised learning for today. That is very much similar to multiple linear regression, where we have a predictor Y and we have different descriptors X1, X2 that we can use a linear regression to correlate and eventually reach the equation. Once we know X1, S2, etc., then we can calculate the Y. So that's a traditional multiple linear regression. But for machine learning, there's some similarities but also some differences. One similarity is we also have these descriptors as our input. Now we can have this input in different features and in different formats. I'm going to show a little bit more later. We also have this output, but this output, in addition to being a regression, we can also do clustering, meaning we can cluster, let's say, contaminants into different groups, or we can cluster microplastics into different types. Those are typical ways of doing clustering. And similar to multiple linear regression, now we have different algorithms. This can be linear, can be nonlinear. That's where machine learning tools come in to really correlate these input features with the output features. So this is a general idea of how we develop machine learning models. And if you want to learn more, here is the paper you probably want to kind of read a little bit more about. But there's some specifics that we want to emphasize when it comes to modeling chemical reactions. For chemical reactions, firstly, certainly we are also going to have an input data set that's needed. And usually this data can come from literature, coming from experiments, or coming from simulation, right? We want to obtain very high quality data set that has as many samples as possible. For now, we actually have a lot of limitations in what kind of data we can have, because if we want to extract the data from the literature, there is very time-consuming and labor-intensive. We have to manually collect data from one paper after another, and then decide which data are of high quality. Excuse me. But then if we design experiments or simulation, there's only that kind of time we have, right? We cannot spend 5 years to get one project done. So there's always a limitation in how much data we can have. But once we have sufficient amount of data, then we can continue to say, okay, how do we either manage the data or clean up the data? Let's look at the reaction kinetics as an example. Here we look at how chemicals are degrading over time. So based on these kinetics, we can calculate either reaction rate constants like K value, or we can calculate the percentage of conversion at a given time. Sometimes we can easily set up a threshold. Let's say it's above 60% degradation or less than 60% of degradation. That's sometimes even used. Once we have that data, then we can set up to this Excel sheet. So this can show all the data we have so far, right? The first column can be different chemical names. The second column is how we can convert these chemical names into smiles, which is a way to capture the chemical structure so computers can read them. We can also have to include these different reaction conditions. that's such as pH, ionic strength, temperature, etc. And then the last column is going to be the rate constant. Of course, in reality, we have many more features included in the input just to capture like reaction conditions, if we have some descriptors or other things. But the idea here is we want to include as many features as possible to capture the reaction we're looking at. If it's oxidation, right, we want to see what the features can reflect oxidation. If it's biodegradation, you know, how is the biodegradation mechanism somehow being captured in the input? So this data curation, data cleaning is a critical part of ensuring high quality model that we can develop later on. Of course, one thing that we need for the near future is, can we have machine learning tools being developed that can help us mine data from the literature and also design new experiments or simulations? Because for now, the manual approach is going to be very limited. So if somebody has experience or expertise in this area, that's going to be very, very important. So here, once the data is available, we can move on to develop the model following these 4 different steps. The first step is how we capture these input features. I'm using chemical representation as an example. There are 6 common ways to describe chemicals. I'm going to show more examples next. Once the chemicals are captured, then we want to capture reaction conditions, the system descriptors, etc. And then we decide, are we going to model the reaction kinetics, or how fast the chemicals are either disappearing or forming, or we can even capture these reaction pathways, right? These are different products being formed and how they are formed in sequence. For today, I'm going to focus on this monitoring reaction kinetics. Once we know our input and output, then we'll move on to the model development, where we have to select different algorithms that work for this particular data set the best. Then we have to optimize the algorithms, tuning the hyperparameters. Once we get a good model, we have to validate the model performance. I'm going to show more on this validation process next. And finally, we want to define how well these models can be applied in a given scenario and whether any reaction mechanisms have been correctly learned by the model. So this flow, if you are familiar with the machine learning model in general, you know, this is very much similar in many different general ways, but there are some specific details we have to pay attention to. So here's a little bit more about the chemical representations. I'm showing 6 common approaches for 2 different chemicals. If you look at these 2 chemicals here, one is a bisphenol A and the other is tetrachlorobisphenol. The first way is very simple. We just simply count for each chemical how many function groups each chemical has. For example, for OH group, for the first chemical has 2, the second chemical doesn't have any. For chlorine, the first chemical doesn't have any, the second chemical has 4, right? That's a very basic way of describing chemicals. The second one is using different molecular descriptors. There are definitely many computational calculations that we can do. One thing we find is very useful is something called the PADL descriptors, where there are over 1,000 descriptors being provided by this particular package. And it has been very useful for us so far. The third one is also something we use quite often, that's molecular fingerprints. So each line here, each set of these descriptors representing certain function groups or certain substructures. Each one here represents one substructure and 0 represents as no substructure for that particular location. The fourth type is simply using SMILE streams, which usually we have to rely on this text. So this is like text information as an input for chemical structures. We can also capture these images as a graph using edges, nodes, so we can really look at the relative positions of each atom in space. And finally, we can capture them as even images. So you see there are so many options, but so far we don't know if any one of them is particularly better than others in any given scenario. So we might have to compare their performance for a given application. And also note that in the center, I showed quite a few different algorithms. So in general, more complex chemical representations would require much more complex like algorithms. For example, if we have to work with neural networks, such as convolutional neural network, we need images. For graph, we have to need like graphical neural network. If it's a text, we have to use recurrent neural network. But for many cases, if we have a smaller data sets, neural networks might not be a good choice. Then we have to rely on this tree-based or even simpler algorithms like a linear regression, lasso or ridge, etc. So this is very much a try and error and also a optimization process to decide the best combination of chemical representations and algorithms. Once a model is developed, we have to decide how good it is. That's called a model evaluation. Very common, we firstly use at least two different matrices, such as R-square values or root mean square errors to decide if the model performs well. But we don't want to stop there, right? Because those matrices are not being compared to the state-of-art models that are widely used in the literature. So we would like to add two more steps of evaluation. The first step is to compare with some base models, such as linear regression or k-nearest models, which do not really rely on many assumptions and are very easy to run. If the model does perform better than these base models, then we can compare to the reported models in the literature. So that means we have to compare their performance on the same data set. Remember, we cannot compare two models if they are developed on different data sets. So we want to compare the models with reported ones, but you might want to run them on the same data set. It's only after all these three steps, then we feel more confident saying this model is a very good model. And last thing, well, not last thing, but the next thing is to define how well this model can be applied. So a simple way is to draw these lines to define the space of these chemicals. So that means this, if the chemicals like located inside this space, we say this model can work very well because the space is determined by what kind of training chemicals we have. If test chemicals are also located within the space, we say that these chemicals can be very well predicted. But if we chemicals like shown in red outside the space, then we might have less confidence and more uncertainties in the prediction. There are certain ways to define this chemical space or applicability domain. I showed a few examples here. But of course, if you read the papers, none of them are really perfect. So we have to, again, probably try different ways or have to also validate the applicability domain later on. The next thing is going to be very important. That is probably not being emphasized enough in the literature. That is the model interpretation. There are two different ways to do model interpretation. The most common way is to evaluate the feature importance. I'm using this Shapley value as an example. Of course, there are a few other ways to do model interpretation. Basically, we want to say if the models have learned correctly the reaction mechanisms. For Shapley value, it's not a necessarily easy one, but once you get to know it, it's not that hard. So essentially, each line here represents one input descriptor. So I'm going to use this BET surface area as an example. You see the Shapley value with 0, it simply means there's the average importance of all features. If the Shapley values are on the positive side, that means their importance is more than the average or they are more important, so they can contribute more positively to the final prediction. When we have a negative Shapley values on the left-hand side, these are negatively impacting the overall reactivity. So if we look at the BT surface area, on the right-hand side, we have the red colors. These are showing the high BT surface areas. In this case, high surface areas can increase the reactivity. And on the left-hand side, we have these blue colors. These are meaning lower BT surface area will decrease the reactivity, which is somehow not surprising to us. But less often, we also can determine how each training sample contributes to the overall reactivity. And one example we have here is called the influence function. So basically, we compare the model performance with a given sample included and without a given sample included. The difference between these two will be the overall importance, right? If a sample is very important, if we don't consider it, then the difference in the model performance will be dramatic. So in this particular example, I'm showing where we have about 2,000 chemicals in the training data set. And the performance is on the left-hand side, showing in this reddish bar. If we now exclude 5 chemicals, or in other words, we have 1995 chemicals in our data set, the purple showing if we exclude only 5 chemicals randomly. So if you see, compare the first and the third bar, really we don't see much difference. So that means randomly excluding 5 chemicals does not impact the model performance, which is not surprising, right? Because we have a large number of chemicals already. But if you look at the middle bar where we exclude 5 chemicals that are the most similar to the chemicals we're interested in, we call that the nearest neighbors. And you see that the larger increase in the root mean square error, that means there's a large increase in the errors, or much less, there's a much less good performance we have. So that certainly demonstrates the importance of these 5 most similar chemicals in deciding the chemical performance. This way we can find out, firstly, which chemicals are important for a given prediction, and also how do we improve the model performance, right? By including more similar chemicals to our prediction target. So with that background in mind, now I'm going to move on to the next part of using a larger data set to predict aerobic biodegradation. So why do we care about aerobic biodegradation? I believe nobody would argue that aerobic biodegradation is one of the most important transformation pathways. This is in both wastewater treatment and also in the transformation of contaminants in the environment. To know biodegradation kinetics, we have to do different biodegradation tests. Once we know their kinetics, there are 2 major usages of this information. One is for new chemical development, because new chemicals are regulated. If they are deemed biodegradable, then they can really easily pass through this regulatory screening process. They can be kind of used in a commercial sense. But if they are not biodegradable, then more stringent requirements will be put on these chemicals to avoid their potential risks. Another is for the existing contaminants. If a site is being contaminated with a contaminant, if we know biodegradation occurs, then we are less likely to worry about contamination. But if these chemicals are very resistant to biodegradation, then we need to formulate the treatment strategies accordingly. However, to do this biodegradation test is very time consuming. Anybody who has run biodegradation tests, you can only run a few samples at a time. It lasts very long. So it's not many tests you can do. And even for some standardized tests, they're very expensive. Based on our communication with the industry in the US, it usually takes somewhere even 3,000 to 8,000 per sample. So that means this machine learning is going to be a promising alternative to allow us to predict aerobic biodegradability. However, there's a lot of limitations in the current machine learning models in this space. Firstly, all of them have very small data sets. The best one we have is about 3,200 chemicals. And most of them actually have a few hundred chemicals. Majority, almost all these models are only for binary classification. That means they can only predict either they are biodegradable or non-biodegradable, which is very arbitrary to set up the threshold to see which ones are biodegradable. And most also, now these existing models consider the reaction conditions. So if you think about different sludges we're using, different site we're using, different pH or temperature, you can really recognize the current predictions are going to be very, very basic level. So really there's a great need to a more accurate, widely applicable models. That's where we come in. So we firstly collect a larger data set. So this is really the largest data set we ever have. I wouldn't call this a big data set, because I was talking to statisticians and they were joking. If you feel your Excel sheet can handle your data set, well, that's not going to be a big data. So I'm not going to call this a big data, but a rather large data set. But at least we have over 12,000 records in this data set. We clean up, curate, include the reaction conditions as much as possible. In this case, our output is the degradation percentages at a given reaction time. And then we continue the training, as I showed you earlier, by using different representations, using different algorithms, and then tuning the hyperparameters, etc. Once the model is being trained, then we continue to do model interpretation. This is for regression model, where we can predict the percentage of degradation at a given time. But in the industry and regulatory agencies, a more often application is to classification, where they want to firstly know, are these chemicals biodegradable or not, based on certain cutoff points. So we kind of refine this regression data set to become a smaller classification data set, because now we have to set up reaction time at 28 days and remove all these other time points. So there's much less data being included. And in this case, our output is only 0 and 1. 0 represents biodegradable and 1 represents non-biodegradable. We continue to do the model tuning and training. In the last box, we're going to, for both models, we determine their applicability domain and apply to a larger data set that is being operated by the US EPA, includes more than 850,000 chemicals. And finally, my student was smart enough to develop 2 free online predictors that allow users who don't have much machine learning background to still be able to apply these models. So just quickly showing the performance of the models. The left-hand side is showing the regression model. When we plot this predicted value versus the true values, the R-square value 0.54. So the spread here is not impressive if you think about, still quite large errors. But given the variety of the chemicals included, variety of conditions, we're quite happy because really no other models can do this much of regression performance yet. And in general, regression models are more challenging to develop compared to classification models. On the right-hand side is the performance of classification model, where we achieve an overall performance accuracy of close to 89%. You can see in these 2 different colors, very well we can predict whether a chemical is readily biodegradable or not. Compared to the literature, usually much smaller data set, and the accuracy is almost always less than 85%. But in addition to the performance, we still were wondering, does this model learn correctly the reaction mechanisms? One thing we look at is, can this model learn the contribution of individual functional groups? In this case, let's take this benzene and nitrobenzene as an example. We know nitro group is an electron withdrawing, so the presence of nitrate or nitro group will inhibit biodegradation. But can this be learned? So we compared this feature importance. So we basically select a few common substituents that we know have a certain ability to impact aerobic biodegradation. The x-axis is the known contribution based on group contribution method, and the y-axis is our contribution based on the existing model. And if you see this fairly good linear correlation, so that means this model really learned about these contributions of individual groups very well. You see this carboxyl group, this OH, these hydrophilic groups, they tend to improve their reactivity, and these electron withdrawing groups tend to decrease the reactivity. Once we have more confidence in our models, now we apply to a much larger data set. This is DSS tox data set that has over 850,000 chemicals. It's very interesting that out of these 850,000 chemicals, only 1.6% we do not have very good prediction for. For 98.4% of the chemicals, they are all very much similar to this data in our training set. So the accuracy can be as high as 88.6 and as low as 73.2, depending on how similar they are to the chemicals in our training data set. So in overall, for this part of the research, we have a much larger data set. We have both regression model and a classification model. And also, I didn't mention, but we do have online predictors that allow us to predict this aerobic biodegradation without knowing machine learning knowledge. So I have this website here if you are interested in it. For the last 10 minutes or so, I'm going to introduce the second example where we are facing small data sets and we still have to develop machine learning models for. We're showing these 4 different common oxidants: hydroxyl radicals, sulfide radicals, hypochlorite acid, ozone, and chlorine dioxide. These are all very important oxidants we're using in advanced oxidation, in disinfection, and in many different environments. So general background for these traditional models, where we have this quantitative structure activity relationships, where we can correlate the chemical properties with activities such as oxidation kinetics, right? Commonly we use a multiple linear regression, which I showed earlier has multiple limitations. So last couple of years, we already developed 2 different models for hydroxyl radicals towards over 1,000 chemicals. The top model is based on deep neural network and molecular fingerprints. The bottom one is based on convolutional neural network and molecular images for chemicals. So now we're moving on to 4 additional oxidants we're interested in, including sulfide radicals, HClO, ozone, and ClO2. Well, we started with the same approach as we used for hydroxyl radicals, but the first thing we realized is that now we have a much smaller data sets. For OH radical, we have over 1,000 chemicals, but for this sulfide, 342, for ozone, over 400, but for ClO2 and HClO, we have less than 200 chemicals. For those small chemical data sets, the existing machine learning models might not work very well. So we have to explore additional approaches. Currently, there are 3 mostly common used approaches for handling small data sets. The first, or the most important one, is called the transfer learning. This is really based on another model. So we have a different data set, it's much larger. Based on this data set, a model can be trained. Now, this model has knowledge being learned from the previous data set. Now, if we have a small data set, we can further tune this model with this small data set. So the knowledge being learned previously from the large data set is embedded into the small data set, and this kind of a transfer learning will significantly improve the model in performance. The second idea is to augment the data or systematically increase the data sets. For example, if we have a chemical images, we can flip the images, we can rotate the images. This can increase the sample size. Of course, there are different ways, right? You can use, there are a few other computational ways you can increase the sample size. But this also has some limitations. We can only increase the sample size within the current chemical space. We cannot go too much beyond the current chemical space. The third approach is called a multi-task learning, where instead of running one data set or one model at a time, we can pair them up so this model can learn from all 3 data sets simultaneously, and then the final predicted outcomes will become this kind of combination of all these three data sets. Essentially, if we use this hardcore learning, where these hidden layer parameters are being shared among the 3 data sets. So these are common ways. But when we tried all these 3 different approaches on our small data sets, we have a small improvement in the performance, but none of them really dramatically improve the model performance. There's another way we recently learned about active learning. So essentially, for active learning, we can start from an initial small data set, as shown in the black curve, within this black curve. With the small data set, when we develop a model, make predictions, and then we select a few new chemicals that have predicted values, and also we can experimentally or computationally obtain their reactivity. Now we can add these new chemicals back into this initial data set, as shown in this red line. So we have a larger chemical space now. And then with this larger chemical space, we retrain the model, and do further prediction. So after a few rounds of these, this model can be significantly better, covering much larger chemical space and without too many experiments or simulations being conducted. So this is a very interesting area for us to go into in the near future. But in this particular work, we explore two different approaches that has not been used previously. The first one is a little bit similar to that multitask learning, but we, instead of using multitask learning, we combined all those data sets together into one major data set. This is because we assume that these are all oxidation reactions. They should share some common knowledge, right? Such as electron transfer, such as activity of different functional groups. Once we have this larger data set, we call that unified data set, then we can follow the same procedure as we did earlier, using different representations, remove outliers, overfitting control, tuning the parameters, and developing the model. This is the first approach. We also used a second approach where we want to transfer knowledge between two data sets that are most similar. So in this case, take this CO2 model as an example. So we first develop a model based on CO2 data set. Then we apply this model to the second data set like ozone, predict the chemical reactivity in the ozone data set. So now these chemicals in ozone data set has the reactivity towards the CO2. We add this CO2 reactivity into the ozone data set. And now we're hoping that knowledge being learned from CO2 data set is embedded in the ozone data set. Then we call this knowledge transfer-based model. And we're hoping this model can perform better than just developing ozone model by itself. So first, let's look at what the results are for single models. You see for sulfur radicals, they have the lowest root mean square error. But for HCl, ozone, and CO2, they both have a poor performance and even larger differences between the training and testing data set. So that means we have more serious overfitting for those small data sets. And then we also compared the performance of molecular fingerprints and descriptors. Descriptors in showing green tend to be better in most cases, but it's not performing well in some cases. So which descriptors or which representations is good really depends on the application. Usually we have to screen different representations to find out. But why does this sulfur radical data set performs the best, and how we improve this? So to do that, we have to interpret the model to see what has been learned. One example is to look at the pH effects. So we know pH has a significant impact on the reactivity. Let's look at the sulfur radicals as an example. Here, for these red dots, this means the high pH values. They tend to have a positive Shapley values. It means high pH favors the reactivity. The blue dots are on the left-hand side, means with lower pH values, lower the reactivity. This is understandable because oxidation is removing electrons. So if we have electron-rich chemical, they are more favorably reacting. Like if you have a phenol becoming phenolate under higher pH, certainly the reaction becomes faster. So that explains this pH effect. For ozone, we also have a similar pattern. The red dots are on the right, blue on the left. For CO2, similar red dots on the right, blue on the left. So the pH effect has been correctly learned for these three chemicals. For HCl, you can see it's actually interesting, very much opposite. We have the blue dots on the right, meaning these lower pH values actually improve the reactivity. But if we look at the reaction, it's not surprising at all because HCl is an acid-base reactive species, becomes ClO- under higher pH. ClO- is actually a much weaker oxidant compared to HCl. So that means if pH is less than 7.5, we actually have a higher reactivity, which is correctly learned by this model as well. So that's interesting, right? The model is kind of smart. And then next, we are looking into how different functional groups are being viewed as important in each data set. I know this is kind of a busy kind of figure to look at, but just paying attention to the general pattern. For each of these oxidants, we listed the top 9 most important structural features. You don't have to see what each structural feature is, but look at these dashed lines. Each dashed line means the common features being learned among different data sets. So the general impression is we do have these common functional groups being deemed important in these different data sets. That validated our proposal that we can use either unified data set or transfer learning or knowledge transfer to build up better models. However, if we look into the contribution of each functional group, we actually find some differences. So the highlight here is for aromatic carbon. You see the arrow means, the green arrow means for sulfide radical, this aromatic carbon can increase reactivity. But for the other 3 data sets, we have this down red arrow, meaning they are decreasing reactivity. In reality, we know aromatic carbons can contribute positively to the reactivity. So it turns out only this sulfide radical data set, the model has learned about the impact of aromatic carbon correctly. In the other 3 cases, they didn't. So because this wrong information being learned, the performance of these 3 models was not very good. But there's a way to improve that. One way to do that is to merge small data sets. You see, when we have a unified model, we have overall performance showing in the scatter plot where we achieve RMSE of 1.62, R-square value of 0.76, much better than previously. And if we compare this unified model showing in green versus individual model showing in red, we see for all the 3 data sets, we have improved the performance by this lower root mean square error values. So we went further into interpretation, find out that's because the aromatic carbon has been correctly learned as a functional group that can improve the reactivity. But for sulfide radical, somehow the performance becomes slightly worse, because now for sulfide radical, the aromatic carbon is not being as a positive contributor. So somehow it's being learned actually incorrectly in this case. So finally, we'll look at effect of knowledge transfer. Does this work? It's interesting that it works sometimes, but not all the time. So look at the first pair comparing ozone and HClO, we see the improvement in the performance because they are sharing this common functional group in both data sets. So this common shared group can improve the knowledge transfer. In the middle here, we see for one group, the improved performance, but for the other group, we have this worse performance. This is because they actually learn the effects of these 2 groups oppositely. I mean, this group oppositely between these 2 groups. And finally, if you look at CO2, HClO, we don't see any improvement or any changes in the performance because there's no shared features between the chemical groups. So essentially, the knowledge transfer has to depend on whether these 2 groups have shared features so that they can learn from each other. Overall, I have to say that, machine learning is a very powerful approach, especially for modeling chemical reactions. For large data sets, it's slightly easier to develop models. For small data sets, we have to use different approaches, transfer learning, unified models, etc. But we do want to emphasize this knowledge transfer, although it didn't work that well in this particular case, we believe it's a good method moving forward, because if you have small data sets, you can still benefit from transferring knowledge from one to another, rather than always you have to start with a larger data set. These are other papers we published in the past couple of years looking at the different aspects of machine learning modeling, hydroxyl radicals on the left-hand side, reduction here, and then adsorption. And then we also have another model looking at heavy metal adsorption. So before I finish, I want to advertise for this special issue I'm organizing in ESNT Water that submission deadline is March 31st. Is application for AI, machine learning, data analytics in water environments. Many examples I'm showing here, but can go much beyond these examples. Anything that has water involved will be very much fit into this special issue. So if you have any questions would like to submit, please let me know. We're welcoming all submissions. Thank you very much.
All right, thank you very much, Professor Zhang. I think a very interesting talk. So there are some strategies for the machine learning. It's great. So any questions? So
Do you allow
do this.
questions, do you have to ask questions directly, or they have to type in questions?
Yeah, I think some people like to type in, and maybe some people can raise their hand. Let's see.
Okay. Yeah, either one would be fine with me.
Sure. Let me see. Yeah. So maybe I can ask a quick question. For the data set, as you said in your talk during your presentation, so it's because I think more data set is better for the prediction, right? So is that so all the data you collected is from the for example, a search from the Web of Science or some other like Google Scholars, right? So it's manually, or you can write some code to search.
For now, we're only doing manual collection because we're not a computer scientist. Writing code will actually take much longer time. And more importantly, we have to really do this data screening. For each paper when we read, we have to decide how good the quality is. Do they have controls? Do they have replicates? Do they fit into the criteria we're having to meet this quality insurance? So that's why we have to do the manual collection. It turns out this data collection, data curation take the most time. Once the data is ready, actually the model development is relatively simple.
Okay. All right. Thank you. Yeah.
Yes.
So it's still time consuming.
Yeah.
Right. Yeah. Data collection is the time consuming part.
Yes.
Okay.
And also data collection, not just simply you collect data, that's where you have to use your domain knowledge, right? You have to know certain reaction mechanisms. You have to decide what will be important features to include, especially if you move on to look at the reaction conditions. How do we capture the reaction systems? How do you describe whether it's oxidation, reduction, or biodegradation? Those are all important things we have to include into the model. And writing code, I don't know if they can really include such kind of information at this point.
Okay, yeah, that's right. Right. So any question, if you have a question, you can just type into the chat. Oh yeah, it's from some people is typing in. It's how to implement TL.
I believe that's a transfer learning. How to implement, I think, traditionally transfer learning is mainly based on neural networks. So you just have to start from a larger neural network model. I think there are existing packages you can download and then do further tuning. But you have to also decide which neural network or which transfer learning data set you're going to start from, right? It can be general image net, which is general images, or newest one, we have this chemical net, where there are existing models being developed based on over 1 million chemical images. So that would probably be more realistic compared to just from general images, right? So you have to decide where to start, and the details, I don't do modeling by myself, but my students can really help you if you need it. There are a lot of tutorials of how to realize transfer learning.
Okay. Yeah, the second question is written in Chinese. So what they said is that the data collected from your experiment to do the machine learning, is that more novel or not? But yeah, I think it's very difficult, too much data, right? If you all do all the experiments.
Well, where you get data probably doesn't mean whether it's more novel or not, right? It's the data quality itself. So if you can design a unique set of experiments to answer a particular question, certainly that is creative. It's just a research question is asking not where you get data become novel enough. So I hope that answers the question. But based on my experience so far, I feel there's always a limited data in the literature. So you might just have to design your own experiments to have your unique data set and to target a specific question. And that's going to be very important.
The next question is, can you explain Shapley value?
Yeah, let me just give you that slide again. I know that's kind of not easy to understand. It took me a while to know how to, I don't know if I can explain that well. But Shapley value is, so if you have a Shapley value of 0, that is the average performance or average score of all features, or average influence of all features on the model prediction. But if a feature has a more positive contribution, then it's going to be a positive Shapley value on the right-hand side. On the left-hand side, these are negative Shapley values, means these features, their importance is less than the average, right? That's the first thing you're looking at. The second type is the color of these Shapley values. As shown in the scale here, the red colors meaning these are higher feature values, or meaning for BT, the red means higher BT values and the blue means lower BT values. And now you can look at whether the higher BT values have a positive value, Shapley values or not. In this case, these red values, meaning positive BT values, they have a positive Shapley values. So that means higher surface area contributes positively to the prediction. That's how you can read the Shapley values. Hopefully that's help you a little bit more.
So can you see the question? So there are more, actually there are lots of questions now.
Oh, yeah, okay. Okay, let me just try to answer these questions. The next one is how to use, I think this data that doesn't have enough features. So that's going to be the major limitation if you have the development model. Doesn't matter how much data you have, usually the more the better, the more diverse the better. But if you even have a very large data set without some key features being included, I'm afraid the model will not perform very well. So this feature engineering, to me, is probably the most important part of the model development. If we really truly have a big data, probably feature engineering becomes much less important. But for us, we always handle the smaller data sets, and that's exactly when this feature engineering becomes the critical part. And next one is compared to linear LM, linear models. Using machine learning often leads to overfitting issues. I completely agree with that. That's why you have to use a lot of overfitting control. You have to have a proper evaluation and also comparison of different algorithms. So we don't want to overkill, right? We don't want to use a neural network if you have only like a few hundred or even less than a few hundred data points. So simpler models are always preferred if they can perform similarly. Next one is how to find out the good. I think this is for this data augmentation, how to select the good data augmentation approach. I don't feel that's a golden rule regarding this data augmentation. You just have to use a few different ways to compare the performance. To do modeling is very much similar to do experiments. Before you run the experiments, you don't know what the results are going to be, right? This is similar. Before you run a model, you basically probably don't know how model is going to perform. You just have to do it and see, right? That's probably not the best answer, but that's my experience. PHP or SHAP, which one is better? I'm not too familiar with the PHP. I know in our initial paper published last year, we kind of preferred Shapley because it follows two rules that we want to be able to be partial in determining the future importance. But I cannot really tell you what the PHP is, sorry. If you have doubt, go to comparison and look at the basic fundamentals to see that if they are good enough. Next one, how do you create the label of the molecular structure? So the molecular structures, we typically firstly convert all the structures into their smile streams. Usually that's only a lot of phone calls this morning. So usually it's very straightforward. There's existing tools, one live code can easily convert all the smiles to smiles. And then from there, you have to decide whether you have, you want to use the fingerprints, images, descriptors, right? There are different ways to convert, or you can simply use smiles as text itself. For now, based on our experiments, we definitely don't know what the best representation is, and we tend to compare different ways and find out the way we want to focus on for the final model development. Oh, it's PDP or SHAP. So it's a partial dependence plots. I definitely think Shapley is probably more powerful than PDP. But I don't quite remember the details now. My experience is Shapley will give you more information. So next one is about the missing data. Can missing data, if a data set has a missing data, can still be used in machine learning? Yes, there are actually algorithms that can really handle this missing data very well. So you want to focus on usually tree-based algorithms are very good at handling missing data. Of course, if you have 80% of data missing, that probably means you cannot have that as a good feature. But some like tree-based usually have very good ways of handling missing data. For this data augmentation, how do we evaluate the performance? So I feel the best way to evaluate the performance of data augmentation is you have to select a few represented augmented data and using either experiments or a separate simulation to verify the quality. Because we cannot use the model itself to evaluate the performance, right, of the augmented data. You just have to be a separate way. If it's a reaction kinetics, we can use experiments to perform it. If it's like a computation calculation, then you have to do another simulation. So basically, to know whether this augmented data is good or not, it has to be independently evaluated. So next one is, what's the function of the model? Is that only limited on data collection? Not quite sure what that means. I think it probably means how would the quality of the model, I would assume that's what it meant, right? Is that only limited on data collection? So, well, I think the majority of the work is actually on data collection. When we say data collection, that starts from your question, right? What kind of research question you have in mind? Is it a novel question? Can we have, or can we design experiments or collect enough data? That's exactly what our expertise comes in. So that's why computer scientists cannot work in our field, because they don't know our research, they don't know our applications, they don't know our data. I hope that's what you're asking. Is the Shapley value similar to correlation coefficient? Not necessarily. Correlation coefficient simply means the performance or the relationship between the predicted versus the experimental or computational values or true values. Shapley values are usually the ones describing the importance of the input features, right? If you have a pH, we want to know how important the pH is in affecting the chemical reactivity, whether high pH is favorable or lower pH is favorable. That's what the Shapley values tell us. Feature importance. Any comments on data imbalance approach? Yeah, that's a very good comment. So very commonly we see data imbalance. That means we have a lot of data focusing on specific like types of chemicals or in a small database, a small chemical space, or in a small region of the chemical space or in application space. So we try to balance the data as much as possible. There are a few data imbalance approaches. Again, I don't think any one particular is better than others, right? You want to have to do some comparison there. Yeah, I really don't feel there's always no golden rules on any particular approach. A good rule of thumb is you want to do a comparison. The next comment is, why are there more than one Shapley values for one descriptor for one model? Yeah, that's a great question. I forgot to explain. So let's see, we have 1,000 chemicals in our training data set. Let's see, we want to look at the pH effect on these 1,000 chemicals. So essentially, we have one Shapley value for each chemical at each pH, right? So that means we have 1,000 Shapley values. One value for each chemical. That's why there's so many Shapley values. That's why there's a wide range of values sometimes. So another common approach is you can look at absolute mean values if you just want to look at the overall performance or overall impact of that particular descriptor. And let's see, the next question is, what is the limitations of machine learning in predicting chemical properties? Limitations. I think the major limitation we're facing right now is not enough data. If we have small data sets, the models are going to learn just based on their small data sets. One example I didn't mention in one of the slides is when that aromatic carbon was learned, some models actually didn't learn correctly how aromatic carbons contribute to the reactivity. This is because all the chemicals we have in the data set are very reactive. So when they look at the average performance of aromatic carbon or average contribution of aromatic carbon to the overall reactivity, they actually treat that as very high values. Again, that's probably more biased because we have only a few hundred chemicals in our data set. If we have a larger data set, very diverse, very representative of the entire chemical space, I think the effect will be correctly learned. So the limitation mostly is in this data set. But even if we have a very large data set, the next limitation is going to be how well can we capture the reaction mechanisms. All the features I introduced earlier on, except molecular descriptors, they cannot really capture the reaction mechanisms, right? If you look at the reduction versus oxidation, which features can we use to capture those? That's going to be limitation, not because of machine learning, but because our understanding of the reactions themselves. Next one is how to decide if a model is overfitting or not. So the overfitting usually means you have a good performance on the training set, but bad performance on the training set, right? That's pretty much what overfitting means. You learned too much. So how to decide? It's mainly based on the differences in the model performance between the training, validation, and test sets. That's why we always have to have independent data to evaluate the model performance and then compare to the performance with the training set. So the next question is, if we use different software such as MATLAB or Python, which one is better, or do they have any differences? I don't really think there's a major difference among these different apps, but I think Python has some uniqueness because there are so many open packages being developed. Especially for us, not a computer scientist, it might be easier just to take the existing packages and then open up, learn them, and apply to our particular cases. MATLAB, you might have less, and then also Python is free. And next one is using our artificial neural networks if we do regression. So I'm not quite sure what the question is about. You mean simple what? So you mean simple artificial neural networks? Well, yeah, well, ANN can certainly do simple regression, right? That's what ANN is mostly designed for. Like neural networks in general are mostly for regression, for good model performance. When we say artificial neural network, it means only we have very shallow layers. They don't have this many layers, so they tend to be requiring much less smaller data sets, comparatively speaking, and do some simple regression. Yes, that's right.
Yeah, I think that's all. Professor Zhang, thank you again. I think lots of questions. I think people are very interested in your talk. Yeah, since machine learning is very popular, and I think lots of people are studying that, especially in China. So that's the reason why we have so many questions. Thank you very much. All right. All right. So if you have any, for the audience, if you have any further question, you can just email Professor Zhang, or if you don't have her email, maybe you can contact us at EEH. So thank you very much. And also another, thank for especially for the Professor Zhang. Thank you again. And I think this is our the talk series. So if you are interested in our talk, please pay attention to the, like we do the promotion on the, like WeChat, like and also Twitters. So thank you very much. Okay. All right. Good night and good morning. Bye-bye.
Yes, bye-bye. See you next time, hopefully.
Yeah, sure. Bye-bye. Mhm.